All right, recording is happening. I'm gonna move my little bar up to the top. All right, good evening, happy Tuesday. So this is the last week of new material. So chapter 10 is the last chapter. So today we're gonna look at 10.1 and the first part of 10.2. So we're gonna talk about hypothesis testing is totally what chapter 10 is about. And hypothesis testing is super useful. And I've had people use it in their final projects, but it isn't necessarily something you need. But it's something that if you want to, you could always throw it in. So we're going to talk about what null and alternative hypotheses are. We're going to look at type 1 and type 2 errors and what the conclusions of hypothesis tests look like. And then I'm going to explain the logic of hypothesis testing a little bit, and then we're going to stop. We'll do the second half of 10.2 on Tuesday or Thursday. This is Tuesday, on Thursday, and then do 10.3. So there's pretty much no math today. So this is going to be just kind of laying the groundwork for hypothesis testing, and then all the math will be on Thursday. So this was like the best way to break up the 3 chapters into 2 pieces. I've tried a couple of different ways, and this is the one that has worked the best. So we are going to get going. Okay, so hypothesis is pretty much the same thing that it is in science. It's a statement regarding a characteristic. So we would make a prediction or a hypothesis, and then we would do the math to whether to support our hypothesis or to not support our hypothesis. So we're going to look at a single population parameter. So we're going to look at like just the mean or just a proportion. We're not going to be going into 2 or more. So that's something that could happen in 244, but we're not going to do that here. So stats 243, we're just going to stick with the basics. Okay, so here are some claims that you could see. So one of them is that 62% of American adults regularly volunteered their time for charity work. A researcher believes that that percentage is different today. So there's a statement out there or a study out there that shows that 62% of Americans regularly volunteered. But a researcher, he may have collected some samples or done some other groundwork, and he believes that that percent is different. He's not saying if it's more or less. He's just saying that he thinks it's different. So this would be a hypothesis that he's hypothesizing that it is different. It's not 62%. So most of the time we lean on previous studies or something that we know or something that's out there in the world. And then we will hypothesize that it is either more or less or just different. So here's another one. According to a study published in March 2006, the mean length of a phone call on a cellular telephone, so funny, it says cellular, was 3.25 minutes. A researcher believes that the mean length of a call has increased since then. So once again, it looks at a previous study that says that the average length is 3.25, and this researcher has some sort of evidence, and he thinks that it has increased since then. Here's another one. Using an old manufacturing process, the standard deviation of the amount of wine put in a bottle was 0.23 ounces. With new equipment, the quality control manager believes the standard deviation has decreased. So once again, we have old processes, something that they have studied before, and now they have new equipment, and they think things are better with the new equipment. So they're going to take some samples and determine whether or not the standard deviation has decreased, which decreased is better because it means it's more predictable. All right, so that's just the basics. And now we'll start talking about null and alternative hypotheses. So first, with these types of statements, we use sample data because usually we can't access the entire population. If we had the population, we wouldn't need to make a hypothesis because we would just know. We would just be able to sample everything. But most of the time, it doesn't make sense to sample an entire population. Okay, so testing your hypothesis, it's based on sample evidence and probability. So we're looking at the probability that we would get a sample of a certain size, or get a sample that has the characteristics that's a certain size. So if I take a sample, I would say, if the mean was this, what's the probability that my sample would have this mean? That's basically what we're doing. So we're kind of testing it against a confidence interval, which is what we did in chapter 9. Don't worry, we'll do math. It'll become hopefully crystal clear on Thursday. So here are our steps. The first thing we want to do is you're going to make a statement regarding the nature of the population. So that statement would be those 3 things that we had before, or you can state that, there was a previous study that said 48% of all households own a dog. So that would be the statement that we see. And then you're going to say, I believe that that number has increased since that original study. So there's the statement that I made. I'm hypothesizing that more than 48% of households now own dogs. Then you're going to collect your evidence. So you make your hypothesis, and then you collect your evidence. This evidence is going to test my statement. I'm going to determine whether or not my hypothesis is true based on the evidence that I collect. Then you're going to analyze your data and determine whether or not your statement is plausible. So remember, we have our super small probabilities would be unusual. And so we could say that things are different if we get those unusual values. And those unusual values are going to look different depending on our alpha. Remember alpha from chapter 9. Alpha is going to become really important here. Okay. So null hypothesis. It is denoted as H naught. That's what we call this, H naught. That's how it's said. So the null hypothesis is H sub 0, which is 8 naught. This is the statement to be tested. We assume it is true until we have evidence that it is not. So whatever previous study we used, we assume that that's true until we can show that it isn't true. That's called the null hypothesis. Sometimes we'll just call it the null, but it's the null hypothesis. Okay. Alternative hypothesis. This is H sub 1. In this class, you will only see it written as H sub 1. Some other classes, it is H sub A, just letting you know for future reference or for science, if you take a science class that uses these types of hypotheses. But for our purposes, we're going to use H sub 1. This is what we are trying to find evidence to support. So I'm trying to support the statement that more households own dogs today. So my alternative hypothesis was that would be that the percentage of households that own dogs is greater than that 48%. So the alternative hypothesis says how we think it is different from the null hypothesis. Don't worry, we're going to do some examples. Okay. All right. Here's the different ways that we can set these up. If I say that I believe it is different, this is equal versus not equal, or if it says that we think it is different, it is a two-tailed test because it can either be greater than or it can be less than. It's just not equal to. So if I say that I believe it is different today, then it could be more than it used to be, or it could be less than it used to be. We just know it's not equal. So that's a two-tailed test because we have areas above and below the mean that could be possible. So if I say that it is less than, I believe it is less than that today. This is a left-tailed test. I'm going to draw little diagrams here. So with a two-tailed test, I'm going to highlight, maybe if I can find the highlighter. So with a two-tailed test, we'd have our center in here. This would be the okay area. And then this would be, it could, land up here or it could land down here. With a left-tailed test, it would just be, we're looking at less than. So, whoops. All of this area would be okay. But this down here would be our area of interest that we're looking at. Does my sample land down here? The two-tailed, it could land here or it could land here for us to say that the null hypothesis is not true. The left tail, we'd be checking down here. Right tail is greater than, once again, draw a nice picture. My highlighter. So all of this area would be okay. And this is the area that we are checking to see if our sample lands up there. So we have the two-tailed test, the left-tailed test, and the right-tailed test. All my lovely little normal curves. All right. And we need a moment. We're good. All right. Whip to the next page. So in other words, the null hypothesis is status quo. It means there's no difference. It is always going to be a statement of equality. You will always say H naught colon our P or our mu or whatever equals a certain value. So we assume that it is true. We assume it's true until we have evidence to the contrary. We are looking for evidence to support our alternative hypothesis. So we are looking for evidence. I can't do this. So we're seeking evidence that supports the alternative hypothesis. So that's what we are looking for in our hypothesis testing. Okay, let us do some examples. So we're going to talk about whether these are two-tailed, left-tailed, or right-tailed, and we're going to determine the null and the alternative hypothesis. So in 2008, 62% of American adults regularly volunteered their time for charity work. A researcher believes this percentage is different today. If you don't see greater than or less than, and you just see different, this is two-tailed. So this is two-tailed. My null hypothesis is that my P, my proportion of people who regularly volunteer equals 0.62. We pretty much always write the percents as a decimal. It's always going to say equals, and it's always going to have whatever parameter we're working with as the number or the symbol before the equal sign. My alternative hypothesis is we think it is different today. So different is always the not equal symbol. And it could be either greater than or it could be less than. But we think it's different today. Therefore, we would put a not equal sign. And that's it on at least stating your hypothesis and your alternative hypothesis. Questions? I think if I swipe, it's going to give me the answer to that. It does. Yeah, it does. See, mine was better. Gives me the alternative or the null. It gives me the alternative. Mine was better. Questions before?
This is gonna sound dumb, but okay, it's two-tailed
Okay.
and do like it doesn't matter which is in which tail, right? It's
Right.
just a
Yeah,
way
so-
of saying that it's
Yeah, so basically this middle piece right here is like my confidence interval. This right here,
Mhm,
the confidence interval.
mhm.
And so when I get a sample, when I get, I'm going to test my sample, I'm trying to determine If my sample lands here or here, then the null hypothesis, we're going to say it's not true. Then we have found evidence to support our alternative hypothesis.
Okay.
If my sample information lands me in here, anywhere in that shaded area, then we don't have enough evidence to say that the null hypothesis is not true.
Okay.
That's essentially what we're doing here.
Okay. We just have two tails to work with. And if the evidence is outside of that confidence,
Mhm.
then
Then it is.
then it is. Then it
Supporting
is.
an alternative hypothesis.
Okay.
So I'm going to get in, I'll get on the verbiage of that later.
Okay. Cool.
Good question, though. That was an excellent question. Okay. So let's take a look at the second one. So according to a study published in March 2006, the mean length of a phone call on a cell phone was 3.25 minutes. A researcher believes that the mean length of a call has increased since then. So once again, our null hypothesis is always an equal sign. And we're looking at mean length, so we're going to use mu equals 3.25 minutes. So the previous study, our null hypothesis is assumed true until we have evidence to the contrary. My alternative hypothesis, the researcher believes that the call has increased since then. So the researcher believes that the call length is greater than 3.25 minutes. So once again, so since it's greater than, we're going to be checking the right tail. Because the area we're going to check, so a confidence interval isn't it, the regular confidence interval is only considered for a two-tail test because we're looking at just this upper area right here. So I'm checking this right here. This is still going to have a critical value. We're still going to have a critical value, but we're not going to cut our alpha in half, if that makes sense. So remember in chapter 9, we cut our alpha in half, but if it's only a right tail or a left tail, we don't cut that alpha in half.
Got it. Okay. Only in a two-tail would we be looking at
Right.
splitting alpha.
Exactly.
Got it.
Because if our sample information lands anywhere in here, our null hypothesis stands. It stays where it is. We don't have evidence to reject it, so it just lives there still. And if it lands outside of there, so if it landed, and I didn't mean to highlight, but if it landed in there, lands out here, that's a highlighter still. Okay, yeah, if it lands out here, then we can say that we have sufficient evidence to state that the null hypothesis probably isn't true. And I'm going much deeper early on than I normally do. I don't know why, just maybe it's because you're such a friendly audience. Okay.
Okay, so because we think mu is greater in that instance, then we're looking at a right tail. If we thought it was less, then it would be left tail.
Exactly.
Okay.
Which is what our next example is. Except for, yeah, see, I like mine better, but we have our right tail test, we have our null hypothesis. Okay. All right, let's move on to the last one. So using an old manufacturing process, the standard deviation of the amount of wine put in a bottle was 0.23 ounces. With new equipment, we believe that the standard deviation has decreased. All right, so null hypothesis, I'm going to have to be creative on where I am on the page. I'm going to put it up top here. My null hypothesis, so standard deviation is sigma. We think that equals 0.23. Whatever our previous information was, it stands until we show evidence against it. So my alternative hypothesis is going to be that sigma is less than 0.23. because it says they think it has decreased. So if I was to draw my little diagram, whoop, it is a right-tailed test. Left-tailed test, sorry, I just lied to you. It is a left-tailed test because we're checking down here on the left. If my sample information lands me down here, then this would be evidence against the null hypothesis. So this is a left-tailed test. Just remember, the null hypothesis always has an equal sign. The reason I keep saying that over and over is because there's always a number of people on the test who give me a greater than or a less than on the null hypothesis.
Mhm.
The null hypothesis always has an equal sign, always. There's no example that is different. All right, questions? We feeling okay? Feeling groovy?
Good.
Yes, thank you.
All right. Well, hello, Elena, welcome. Okay. Okay, so here's the two good outcomes and 2 bad outcomes. So the first good outcome is you reject the null hypothesis when the alternative hypothesis is true. Whoa, doggone it. Okay, when the alternative hypothesis is true. So if we find that the alternative hypothesis is true, we can reject the null hypothesis. And it says do not reject. I like the words fail to reject. It just sounds fancier, sounds more mathy or sciencey. We fail to reject the null hypothesis when the null hypothesis is true. So if we don't have evidence to show that the null hypothesis isn't true, we fail to reject it. Okay, so I'm going to give you a little, before I talk about 3 and 4, I'm going to tell you, I am pretty lenient on questions that I ask that are about the type 1 and type 2 error. I'm pretty lenient about them. You do have to try to answer them. And if it tells you to answer in the context of the problem, you need to use the context of the problem. Otherwise, I'm pretty lenient on these because I frequently forget what they are. And if I forget what they are, I don't hold my students to too high of a standard with them. So just letting you know. So a type 1 error is when you reject the null hypothesis, but the hypothesis is true. So if we have sufficient evidence to show that the null hypothesis is true, but we reject it anyway, that's a type 1 error. And then number 4, if we do not reject the null hypothesis, but when the if we do not reject the null hypothesis, when the alternative hypothesis is true, this is a type 2 error. So we have sufficient evidence to reject the null, but we don't reject the null. That's a type 2 error. So just make sure it's in your notes. I can guarantee there is going to be a question on the test about this. I'm pretty lenient, but there will be a question about it. And the quiz, I believe there's a question on the next quiz about it. I believe. All right.
Melissa, so for the type 2 error, you'll accept sufficient evidence to reject, but do not.
Right. Yes.
Okay, got that. Thank you.
You're welcome. Okay. Can I move on, or does anyone need another moment?
I'm good.
I'm good.
All righty. Okay, so let's talk about what a type 1 and type 2 error would look like. These get really confusing. Their wording is not great. So I'm going to do the best that I can to help you here. So this is the volunteer time. So 62% of the Americans regularly volunteer their time for charity work, and a researcher believes that this percentage is different today. So a type 1 error. So So the researcher concludes that the null hypothesis is not true, yet it is true. This would be a type 1 error. So basically, the researcher concludes that the proportion of Americans that participated in charity work was not 62%, but it actually was 62%. This would be a type 1 error. So a type 2 error is if we had evidence to believe that the current percentage of Americans who participated in charity work is not 62%, but we stated that it was 62%, then this would be a type 2 error. I know it's confusing. Just do the best you can. Let's take a look at the next one. So in March 2006, the average length of the phone call was 325. We believe it has increased since then. So type 1 error. So our sample evidence, the researcher concluded that the average length was greater than 3.25 minutes, but in fact, the average length of a phone call is still 3.25 minutes. This would be a type 1 error. So he said it was greater than, but it actually isn't. So that's a type 1 error. Type 2 error, he failed to reject the hypothesis that the mean length of a call was 3.25 minutes, but in fact, it is longer than 3.25 minutes. So he failed to reject, but he should have rejected. Okay, let's go to the next one. I guess not. Okay, so there's going to be a question, and it's quite possibly on the quiz, and I'm going to let you know right now. The probability of making a type 1 error is alpha. This is alpha. It looks like a regular A, but this is alpha. Alpha. The probability of making a type 2 error is beta. Even though I do like this page better than the wordy ones for explaining what type 1 and type 2 error is. So type 1 error, rejecting the null hypothesis when the null hypothesis is true. Type 2 error, not rejecting when the alternative is true.
Would it be incorrect to say that we reject the alternative? Can we only reject
You
null?
can only reject the null. You
Got
can't
it.
reject the alternative.
Okay. You can reject or fail to reject null.
Right. Those are your
Okay.
only two options.
Okay.
Good question. Thank you. Okay. So the probability, the alpha is chosen by the researcher before we choose the, what the heck is going on with my computer? I don't know. I'm going to move this thing here. Okay. So we choose the alpha before the sample data is collected. So we choose our level of significance. That alpha is also the probability of making a type 1 error, and the researcher is going to choose that. So you will never have to choose it. So the researcher is going to choose it for you. So don't worry about that, about choosing that. As the probability of type 1 error increases, the probability of a type 2 decreases, and vice versa. They're kind of like inverses of each other. So as one increases, the other decreases. And beta is never again going to come up unless it says, what's the probability of making a type 2 error? Which I think that there's a question on a quiz about that. Just say the probability of making a type 2 error is beta. We'll leave it at that. Heck is this weird box? There we go. So that's all you need to say, is that the probability of making a type 2 error is beta. All right. So this is important. We never, whoa, why is that coloring? I don't know. We never accept the null hypothesis. We don't have access to the entire population, so you cannot accept the null hypothesis. You reject or fail to reject. It's kind of like we don't ever just say that a defendant is innocent. You would just say not guilty. So you can either say we do not reject or we fail to reject. So we reject or fail to reject. Because we can have sufficient evidence against the null hypothesis, but we can't prove that it's true unless we go to the whole population. All right. We're moving right along, man. Crazy. Crazy when you're not actually doing math. Okay. So once again, we March 2016, the mean length of a phone call was 3.25 minutes. A researcher believes it has increased since then. So our sample evidence indicates that the null hypothesis should be rejected. I'm going to show you the wording. Now, the wording is very wordy. You can condense it down a little bit, but it is pretty wordy. So the statement in the alternative hypothesis is that the mean call length is greater than 3.25 minutes. Since the null hypothesis is rejected, there's sufficient evidence to conclude that the mean length of a phone call on a cell phone is greater than 3.25 minutes. Now, if you have stated the null hypothesis and the alternative hypothesis earlier, with your H naught, mu equals and H naught mu is greater than and all of that, you don't need to restate the whole thing here. I usually would just write, I'm going to get a different color here. I would write this. There is sufficient evidence to conclude that the mean length of a phone call is greater than, this is still wordy, but greater than 3.25 minutes. Therefore, we reject the null hypothesis. This is probably how I would answer it. It's still a lot of words, but it's not quite as bad as the other one. You don't need to completely restate your null and alternative hypothesis. Just state that there is evidence to conclude that the mean length is greater than whatever. Make sense? Good.
Yes.
Okay. I know it's a lot of words, and I think that textbook writers get paid by the word. So, I mean, not really, but it seems like it. All right, let's look at the other one. Oh, wait, suppose sample evidence indicates the null should not be rejected. Let's take a look at that wording. Since the null is not rejected, there's insufficient evidence to conclude that the mean length of a phone call on a cell phone is greater than 3.25 minutes. In other words, the sampling evidence is consistent with the mean call length equaling 3.25 minutes. I think that last sentence is redundant. I would probably just say, I'm not going to write it this time, unless you guys want me to. Do you want me to write it or just state it?
Would you write it, please?
Of course.
Yes, please.
Okay.
Thank you.
No
Thank
problem.
you.
I would say, since there is not sufficient evidence to indicate the mean length of a phone call is, that should be an S, greater than 3.25 minutes, we fail to reject the null hypothesis. There we go. Still a lot of words, but not quite as wordy and weird as theirs. And it can be reworded a little bit. As long as I understand what you're saying, I'm going to accept it. But sometimes you got to sound a little bit sciencey.
So does this mean that the 10-1 homework is all word stuff?
I think most of the 10-1 homework is stating is choosing your null and alternative hypothesis. I
Mhm.
believe that that's most of it. Type 1 and type 2 errors might come into play. But yeah, there's no math on 10.1 homework.
Right, cool.
Yeah, it's kind of nice. It's a little bit of a break.
Yeah.
We'll have plenty of math at the end of 10.2 and 10.3. Don't worry. And I know you were so worried about that.
I'm not worried at all.
Like, when are we going to get to math again? All right. Okay, let's move on. Okay, we are now at 10.2. So if you're keeping track of that sort of thing, we are officially at 10.2. Okay, so we're going to kind of talk about what statistically significant means and how we can determine whether we're accepting or failing to reject or rejecting a null hypothesis. So we're going to be doing a little bit of talking about that. So a researcher obtained a random sample of 1,000 people and found that 534 are in favor of banning cell phone use while driving. I guess there is going to be a little bit of math today, just a little bit. Okay. Does this suggest that more than 50% of the people favor the policy? Or is it possible that it's less than 0.5 and we just happen to survey a majority in favor? So would it be unusual to obtain a sample proportion? So remember we talked about unusual of 0.534 or higher if we have a population whose proportion is 0.5. We need to figure out what it means to be statistically significant. That's what we're going to figure out. All right. So, if we determine something is unlikely to happen, remember we talked about that 5% rule. So if we determine that something is highly unlikely to happen, like less than 5%, or it's going to be less than alpha, that's what our determining factor is going to be. If it is less than alpha, less than 5%, or whatever our alpha is, it is called statistically significant. Don't worry, you're not going to be asked to reiterate that word, but that's what it means. If the results are statistically significant, then we reject the null hypothesis. So if the probability of something happening is less than alpha, then it is statistically significant, and we're going to reject the null hypothesis. So that alpha becomes very important. So to determine if something is statistically significant, you have to build your probability model. So we have that our NP times 1 minus P is greater than or equal to 10. So that's always good. Our sample size needs to be less than 10% of the population. That stays the same. And I have a really weird P thing going on here. This is really strange. That says P is, but it just showed up funny. So we take out and look for our standard deviation. So here is the standard deviation based on the new standard deviation, based on the sampling distribution. So we calculated our new standard deviation, and now we're going to determine whether or not it is unusual based on what our population says. So here's the sampling distribution of the sampling proportion. So here's my confidence interval right here. That's my confidence interval right there. So now our sample evidence would be statistically significant if it is too many standard deviations away from the mean. So take a look here. My standard deviation is 0.016. I'm sorry, I'm bumping around. So when I calculate the Z-score of my my random sample, I got a Z-score of 2.15. Since 2.15 is statistically significant because it's more than 2 standard deviations away from the mean, because that is the case, we would have to reject our null hypothesis. So because this ended up being too far away from the mean, outside of my confidence interval, which was basically 2 standard deviations away, the probability of it happening is too small. Therefore, we reject the null. So basically what we do is we assume the null is true, and that's what we base our values on. So if the null is true, then this is too far away from it for the null to be true, that sample. And
Would that be for both ways?
well, since I
Negative.
didn't say it was greater or smaller, this is probably, hold on, I got to go back. We would most likely, we have no hypothesis here, and I just went too far. I know I didn't. So we haven't actually made a hypothesis. I would probably say that, oh, it does. It says, would it be unusual or higher? So this is a right-tailed test. So if I was going to
Got it.
write a null hypothesis and an alternative, I would say, I would not say that. I would make my H naught be that the proportion equals 0.5. That's because that's what we said originally. So this is the 50%. Then my alternative hypothesis, I would say that I think that P is greater than 0.5 because it says or higher. Even though your questions are going to be more straightforward, we're just kind of playing around with it right now. We're going to get more straightforward and have like better standards coming up Thursday. But so
Okay.
I had significant or sufficient evidence, to show that the population proportion was not 50%, that it was probably higher. Therefore, we can reject the null hypothesis. Because we landed, hold on, I landed out here. Because I landed out there, we can say that we can reject the null hypothesis. My Z-score is in that upper area. So we rejected the null hypothesis.
And then, so alternately, if it had fallen inside of our confidence interval, we would fail to reject.
Right. So if I got, even if I got, let's say my Z-score was 1.96, I would fail to reject. Because even though it's up towards the top, it's still not considered unusual.
Okay.
Right. That was a good question.
Good.
Good. Okay. And look, I just did it right here. I could have just used this. It has the probability. So, the probability of it happening ended up being 0.0228. And so let's say that my alpha is 0.05, which I don't have it. We weren't given an alpha, but let's say it was alpha. This probability is less than my alpha. Therefore, I reject the null hypothesis. So your alpha is basically a probability. So remember that alpha is the probability of making a type 1 error. And that type 1 error, I believe it's rejecting the null when the null is true. So if I'm less than that alpha, then we're probably good and that type 1 error is not going to happen. All right, let's move on. This is all exactly the same stuff. Now I have an alpha. Okay, let's move on. Okay, so here's the other approach. So one of them is looking at how many standard deviations you are away from the mean. And I'm going to give you vocabulary to Thursday. The other way is with looking at, one of them is looking at the probability of it happening. The other one is looking at how many standard deviations you are away. So let's talk about the p-value approach. You're not going to have to say, this is the approach I'm using. They will probably in your homework, it's going to tell you which one to use. In the test, I let you choose which one you're going to use. I let you give me either a p-value or it's called a test statistic. So sometimes you get to choose which one you like better. I know which one I like better. We're not going to talk about that. Okay. So another way to do it is just determining the probability of it happening. And that is called a p-value. So a p-value is the probability of it, of getting that value, given that the proportion, the mean, the population mean is 0.5 or the population proportion. So take a look here. So we calculated that probability earlier. So I'm looking for the probability that our p hat is greater than 0.534. So instead of using this, I'm going to look at the probability that my z-score is greater than 2.15. And I got this. So this means that only 2 samples in 100 would give a proportion as high as this. And because that's very small, that's less than 5%, looking at the p-value tells us that the probability is unlikely and we would reject the null. So now this is the way that my high school students remember it. So forgive me. I'm going to write it down. If the p is low, reject the hoe. Remember, high school students, but it helps. If the p is low, reject the hoe. There you go.
That's really helpful.
You know, it is what it is. High school kids love it. One of them came up with it a couple of years ago, and so now I just throw it out there. P is low, reject the hoe. Oh my gosh, kids, gotta love them, right? Okay, our last slide of the night. Told you this was pretty quick. All right, so if the probability of getting the sample proportion is as extreme or more extreme than the one obtained is small under anyway, if I just my thing went small. Why did it do that? I don't know. So if your probability is less than alpha, I'm going to rewrite this, make it prettier. If p-value is less than alpha, reject the null. We're going to do a ton of examples on Thursday. Well, maybe not a ton, but we'll do a sufficient number of examples. Hopefully we'll get it. So it's basically looking at critical values like we did with our confidence intervals. You find those critical z-scores or t-values. You find those critical z-scores, and then you just determine, where does my sample fall? Is it inside that confidence interval or is it outside the confidence interval? That's basically what we're doing. So it does not add too much complication to it. And that's it. That's my last slide. So questions, of course, are welcome.
I don't have questions about this, but I do when you stop recording, if you don't mind.
No problem. Anybody have anything for the recording?
No.
All right, I will stop the recording.